Hi, so far we've talked about currents, measuring currents, looking at currents in the cell as a whole. In the last video, we talked about how to make recordings from single channels, but we didn't really kind of look at those currents from single channels or kind of talk about what those currents mean in relationship to the channel from the whole cell. So that's what we're going to do in this video. Let's go ahead and dive in. What I'm going to show you here, these are the response of a whole cell from a whole cell recording and single channels from a cell attached recording in response to a voltage change. Okay, so again, this is under voltage clamps. So we are changing the voltage. We are going from here negative um, 100 millivolts to positive 50 millivolts. So very negative to very positive. And that is going to be opening these voltage gated potassium channels. They're going to be all closed basically at negative 100 millivolts and more or less open at 50 millivolts. And we can see here, this is and along the y-axis here is time. So what we see here is over time, the whole cell current, it starts at zero. There's no current because these are all closed, and it gets bigger and bigger, and then it reaches a plateau where presumably all the potassium channels are open, and that's what it is. So that's the current. So what are we looking at here? It's the same voltage being applied. Now, each line here is a recording from a different individual channel. And so it's being turned on, it's being turned off here. So here, this is how each of these channels is reacting to this voltage change. Now, before we go ahead and dive in, like kind of, and talk about what this means and how these channels, how you get from these channels to this big current, we really want to understand what these single channel currents are and why they act the way they do. So, my first request of you is that before you go on, that you pause the video here and you just look and you just observe, make observations. How are these single channel recordings different from the whole cell recording of current? Just go in and take a deep look, and we'll go through and highlight some of the main differences and what they mean. All right. So one of the things you might have noticed here is that this trace, it goes as it's going up, it's anywhere from 0 to 2.5 nanovolts. Here, though, we see that the currents are more or less binary. The channel is either off, like it is here, or it's on. And it's up here at 2 picoamps. And this kind of makes sense. If you're recording from a single channel, it's gonna be either closed, right, and not passing current, 0, or it's gonna be open. And here that's that 2 picoamps. And you can see here, like it's either around 0 or it's near 2 picoamps. It doesn't spend a lot of time kind of like in between. Okay. Another difference here is that this is very kind of smooth and predictable. These are kind of random. Like if we see here, like this second trace, it's open, 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 closed, open, 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 open. And we see that all of these, like, and this one, right? It's kind of like slow to open and then it opens and it stays open. So we see that each of these channels behaves differently from each other, even though they're all the same kind of voltage-gated potassium channel. And also each individual channel acts a little bit randomly. So it has randomness, or a fancy term for this is stochasticity, which is the word in the learning objective. And so yeah, it'll be on and then it'll flicker off. It'll be on and then it'll flicker off. And you see this a lot from individual channels that there's flicker and there's randomness. Where does that come from? Well, basically, it comes from the fact that just energy in water, the ambient thermal energy, so like heat in the water, like body temperature heat or even room temperature heat makes water molecules, move around and jitter. And those water molecules and other molecules too, when they move around, they bump into channels, and that those will cause that random movement will affect the channels and make them close, open, and open randomly. And of course, the heat affects the molecules that are part of the channels as well. And so this energy opens and closes channels randomly, even if they're like quote unquote supposed to be in a different state. So we see that here with these channels, they are supposed to be open, positive 50 millivolts. These are voltage gated channels, so these channels are supposed to be open. But you see, even when they're open, this random thermal energy will cause them to be closed briefly for at random intervals. And here's an example of the opposite. This is a channel that is supposed to be closed. So this is a ligand-gated channel. It's not supposed to open when there's no ligand. And most of the time when there's no ligand, it stays closed like it's supposed to. But like randomly, it'll just pop open for a little bit and go back and pop open for a little bit. And so that is also another example of that thermal noise. So either way, you see a lot of this flicker when you look at single channels. You can also see that the size of the current is very different. The whole cell current is in nanoamps. The individual currents are in picoamps. So this is more than 1,000 times as large as the single channel current. And that makes sense, right? You might have more than 1,000 of these channels. And so when they all act together, this is the current that you get. So yeah, each channel will contribute to the overall current when it's open. And so that, putting it all together, how do you get this overall current from this one? Well, it's pretty straightforward. At any given point, you just kind of add up the currents of all the individual channels, and that gives you the whole cell current through that type of channel. And so, yeah, the macroscopic current, meaning the whole cell current, is the sum of the microscopic currents, the individual channel currents. And so, a way you can think about that, I mean, you can think about summing every one of them, but um, to be more precise, you can use this formula, which is one formula that you do need to memorize, although it's not hard. It mostly makes sense, right? Because you can just think of it as like summing up things. So the whole cell current is being contributed to by thousands of channels. The single channel currents, we saw this example here, this particular channel was 2 picoamps, so single channel currents are going to be between like 1 and 20 picoamps-ish. Um, and by the way, 1 picoamp, that's about 10 to the 7th ions per second, if that would be useful, cool for you to know. Okay. So you're gonna add up the single channel currents, and you're gonna right, that's this I, and you're gonna multiply that by the number of channels in total, and that'll contribute to the overall current, right? But there's another factor. A channel can only contribute to the macroscopic current if it's open. And we saw here, like even when the current is at its max and um all the channels should be open, they aren't all. So if we look at this like 20 milliseconds, we see that just because of randomness, like this one and this one and this one and this one and this one are open, but this one is closed just because it randomly did that. And so you have to take the single channel current, multiply it by the number of total channels there are, but you also have to multiply it by the probability of each of these channels being open, right? If only 80% of them are open, you're only going to get 80% of the current that you expect. Okay. All right, so how does that work overall? So say that you're characterizing a mutant potassium channel with cell-attached patch clamp. You find on average your channel is open a total of 8 milliseconds for every 20 milliseconds that you're measuring it, and that the single channel amplitude is 2 picoamps. You estimate using a radioactive K plus channel blocker that there are about 1,000 channels on the cell. So if this is all true, what will be the amplitude of a whole cell K plus current? All right, before we go on, why don't you pause the video, take a stab at that yourself, and then continue on. Okay, so we will want to start with this formula, right? And so each individual current is 2 picoamps. There's 1,000 channels overall. Okay, and what's the probability? It's not given to you directly, but you know that it's open every 8 milliseconds, or 8 milliseconds for every 20 millisecond intervals. So you can divide 8 by 20 to find out the probability. That's basically the probability of it being open. Um, and so if you do all this, you get 800 picoamps, which you can leave like that, or you can convert it to 0.8 nanoamps. All right, I hope that was interesting and gives you some insight about how things that are happen on a very, very molecular level that are um, random can all kind of work together with each other to produce a bigger thing that looks smooth and even and beautiful. All right, thanks so much.